I think I've run into an interesting way to approach what's going on behind the formula for the summation of a geometric series. That's the one where we're simply summing up that r to the k power, and we know if the r is less than 1, strictly less than 1, then and positive, then the answer is 1 over 1 minus 1 over r. The classic example is we draw a square, and then we draw a half a square, and then we draw a quarter of a square, and then we draw a 16th of a square, sorry, an eighth of a square, right? What's going on here is you could stack them together, right? Quarter of a square, eighth of a square, 16th of a square, 32nd of a square. You get that feeling that you're filling in a second square. So the answer is 2, right? That'd be an r equals 1/2. You're halving every time. So the formula ought to give you 1 over 1. Sorry, I have an extra 1 over r here. Apologies. It just should be 1 minus r. So that's 1 over 1/2, which is, of course, the 2. I was discussing a similar problem with areas with a student, and I came up with another interesting way to stack these together that provides another intuitive way to figure out that the answer should be 2. So this is what we were talking about. As usual, we started with a square of dimension 1 by 1. And in this case, we were shrinking both dimensions by 2. In other words, we have something 1/2 height, 1/2 width, right? That's an area of 1 for the 1 by 1, and this is an area of 1/4 because the height here is 1/2, and keeping it on the, keeping the coordinate plane as our reference, 1 and 1/2 or 3/2. And we were looking at what happens when you keep doing this, right? We're quartering an area every time. We're adding half the previous length every time. So this is another quarter added to 1/2. That's 1 3/4. That is 7/4. And so on down the line. The question becomes, how do we figure out the area underneath the total area? How do we figure out that total width if we want to add 1 to 1/2 to 1/4, right? We can add up those lengths as well. We should be able to add up those lengths to something, and hopefully we can add up the volumes, sorry, the areas also. And what we realized was if we took the coordinates here, go up to double the height, all right? This is the coordinate 1, 1. This is the coordinate 3/4, 1/4. We realized that we were simply writing we have an equation for this line, right? This one is, sorry, I didn't mean to say 3/4. I meant to say 7/4, 1/4. This one is 15/16, and only 1/16 uh, sorry, 15/8. Sorry, I see my mistake now. That's 3/2 here, and the height is 1/2. And then as we continue, right, we added 1/4 more to 3/2. This point is the one that's 7/4 at height 1/4. Well, I hope that's enough for you to see that this is a straight line. So we have to stop here. And of course, the equation is y equals 2 minus x, right? Check it. And so that means this point is 2, 0, right? So whoop, we're going down. That's a straight line. All those upper right corners uh, created the line y equals 2 minus x. And we're interested in, well, okay, here we've got, right? Let's take a look at the bottom, right? We've got 1 plus 1/2 plus 1/4 plus 1/8, right? That's the summation formula for k equals 0 to infinity. And here's just powers of 1/2. And we know the answer is 2 because that's where we stop. It's a confirmation of this given formula, a visual confirmation. And then what about the areas? And temporarily, at least, it feels a little bit odd. How are we going to get the areas here? But with this clever trick, right? There's one part, there's another part, and there's another part. These three parts are all equal, and our area, right? The stuff inside the square, that's 2 out of 3 parts. These are all equal parts, right? They're all little triangles, right? Um, 1/2 by 1/2, another 1/2 by 1/2 triangle, and a final third one 1/2. Sorry, I was saying 1/2. Each of these little triangles, the areas is 1/2. They're 1 by 1 right triangles. So we have an area of 1/2, area of 1/2, and finally up here an area of 1/2. Oh, so what we're shading in is actually 2/3. And then take a look here, right? The same thing goes on as you continue down the diagram, right? These are 3 congruent triangles. 1, 2, 3. I'm skipping the Roman numerals for speed. Again, what we have shaded is 2 out of 3 triangles, 2/3 of the total area. So what we're going to have shaded when we take the limit is going to be 2/3 of the total area. 2/3 of the total area. Okay. Well, 2/3 of the total area. What's the total area? Well, the total area is pretty easy. The total area, we got a big triangle that's 2 by 2. So its total area is, right, 1/2 base height, half of 2 times 2, half of 4 is 2. That's 2. But we want 2/3 of it. So we're taking 2/3 of 2, right? We get 4/3 as the total area of the shaded material. Well, let's look at the convergent series, right? When we look at this convergent series, we're thinking about, all right, that has area 1. 1 is our fraction to the power 0. Our next one has area 1/4, right? It's a square. It's a 1/2 by 1/2 square, so that's 1/4. And then the next one, well, we shrank the lengths by a factor of 2, so we're shrinking the area by a factor of quarter, multiplying by a factor of 1/4. And then again, right, since we're halving each side, we're quartering each area. So turns out that our R is quartering, right? Just a scale factor, but it's two-dimensional. Scale factor of a half. Two-dimensional means we're multiplying the area by a quarter every time. And we're adding them all up, and that should equal 4/3. Well, um, let's check it out. 1 over 1 minus 1/4. Well, what's that? That's 1 over 3/4, and that's 4/3. So again, our visual analysis leads to the predicted geometric answer. Now, what'd be very interesting is we can generalize this. So let's try generalizing it. That's going to be the real interesting thing, generalizing. So let's see if we can do that. Right? The idea here would be start with our axes. Right? We're going to start with our 1 by 1. But then I'm going to apply a multiplier that's just R. 0 less than R, less than 1. So all we know is this is some R value, right? There's R. And it's going to be an R by R square. Right? So this is 1 plus R, right? And the height is R. And then we'll multiply by R again. So this is 1 plus R plus R squared, right? This has got width 1, in other words, R to the power 0. This has got width R, R to the first power. This one's got width R squared, R to the second power. And the height, just R squared. Over here, 1, 1, right? Height R, but the x coordinate is 1 plus R, the y coordinate is R. The x coordinate is 1 plus R plus R squared. The y coordinate is R squared. What we want to do here is see if we can see if there's a nice relationship between those points that will give us a line, and hopefully that line will give us the answers, right? If that's a linear relationship, then we can hopefully predict where it will hit the end. Well, let's see. What's the slope here? Over what and down what? Let's take this first chunk, right? We go, sorry, let's take the second chunk because we can do this, right? We go over R and we go down 1 minus R, right? So our rise, we went down from 1, we went down to R. So our rise is negative 1 minus R. And our run is just R. Let's check here to make sure we have a consistent slope. We went from a y value of R to a y value of R squared. So our rise was R minus R squared. sorry, r squared minus r. We dropped r squared minus r. And what did we run? Well, we went from 1 plus r to 1 plus r squared. Ah, but look at that. That has an extra r in every term. So we factor the r out of the top and the r out of the bottom, and we get r minus 1 over r. Oh, I made the same mistake back here. Sorry. R is the small number. 1 is the big number. So the rise is r minus 1. We dropped a little bit. This is the consistent slope. The slope between these points is r minus 1 over r. And we know that 0.11 is on the line. So we can write down the equation of this red line and figure out exactly where it intersects here and exactly where it intersects over there. Let's figure it out, right? Y minus the y value of 1, I'm using this point, equals r minus 1 over r, that's the slope, times x minus the x value. There we go. Whatever mess this comes out to be will be the answer. Let's do some simplification as much as we can. Let's see, y minus 1 equals r minus 1 over r times x minus r minus 1 over r. I'll take a quick liberty here by adding plus 1 to both sides to cancel that out. Plus 1, of course, I can rewrite as r over r. So when I combine these two terms, you'll see I have plus 1 over r. Negative r plus 1 plus r. The two r's cancel here and there. I have the negative 1, the positive 1 over r. So there I've got my slope. There I've got my intercept. So the intercept is 1 over r here. And when I decide to find the width of the triangle, right, this is where it converges, I can simply put in y equals 0 and solve, right? 0 equals r minus 1 over r x plus 1 over r. Well, oops, sorry, I wrote it 2. We know r is non-zero, so let's clear out by multiplying by r. That should make our algebra a little bit simpler. 0 equals r minus 1 times x plus 1 of plus 1. So doing two steps in once, x equals 1 over negative 1 over r minus 1. As we recall, r is smaller than 1, so I'm just going to cancel the negative on top, reverse the bottom, and it'll be 1 over 1 minus r. So we know that our other coordinate for crossing the axis has got an x value of 1 over 1 minus r, and it's got a y value, of course, of 0. I think that'll be enough for us to add up all of the first power terms, and that's really all we need, right? We figured out from the constant slope here that the y-intercept is 1 over 1 minus r. And we also know that the, x-intercept, so I guess I'd better write that properly. Nope, I did write it properly as a x-intercept, right? The x-intercept is 1 over 1 minus r, but the x-intercept is also r to the power 0 plus r to the power 1 plus, hey, this is exactly what we wanted, right? This is the summation from k equals 0 to n of just plain old r to the power k, and the total was 1 over 1 minus r. This is exactly the formula that we used before. There's a geometric derivation of the geometric series formula. Somehow it's shocking but not shocking that you can do this all with geometry. So we're done. We know this works for any r value less than 1. I would argue that if we had r greater than 1, right? If we had a growth factor every time, I'll just sketch that into yellow. If we had a growth factor every time instead of a shrinking factor, we would be able to do something quite similar, although, right, we'd be getting bigger rectangles, bigger squares every time. So if we tried to do the same trick of figuring out where we cross the axis, we would never get a positive answer. The interesting thing is we would get an answer to the left, but the idea of these sums of larger and larger numbers adding up to a negative number, that's kind of disturbing to me. I'd be very interested to see what the geometry would be here, but I wouldn't have any faith in it because in our shrinking, everything represented positive area. When I go to the left of the axis, I start feeling like maybe I'm not. That might be another interesting conversation. Maybe it works out with the extended number line or some other interesting puzzle. But for now, we just go, oh, yeah, obviously, this thing is increasing in area, increasing in length. Everything's increasing, it diverges. In the convergent case, we have a geometric argument about why 1 over 1 minus r is the answer. It's the answer because that's the x value of where the red line crosses, right? And the x value of where the red line crosses is where the sums of r and r to the first and r squared and r cubed and so on, that's where they end, right? These squares always fit under the red line. So these squares are converging down to that point. There we have it.